A vertical container has a base area measuring 10 centimeters by 12 centimeters. That's the base of the container. Now it's being filled with water, and the height of the water is increasing at a speed of 0.5 centimeters per second. So a lot of times in calc problems, we like to draw what the situation is at one particular instant in time so that we can analyze how it may change as time goes on. So let's say that our water height is there currently. Now let's draw what's happening. The water level is increasing. So I'm going to draw a new level that it could rise to from where it was. We have a certain volume that's in the container. Could call it V. Then we also have this slab of water that's being added, which I could point to now and say that this part of the water represents dV. Now, not only that, but there's also going to be a height. This is something that could be relevant in the problem. I'll call it h. And then this little piece would then be called dH. Okay. It says the density of water is 1 gram per centimeter cubed. We want to know at what rate is the mass of water in this container increasing. All right, so one other thing we might label is perhaps a length and a width for our base. Our base would also have an area, A, which is L times W, and that would be 10 centimeters times 12 centimeters, 120 square centimeters. Now, we want to analyze how differentials are related to each other. So, first of all, let's come up with some geometry formulas that could be relevant. That's always a good start. How do we find a volume? Length times width times height. So a couple of formulas I used already. Area equals length times width, and volume equals length times width times height. Now, you want to ask yourself, it's a good question to ask, what quantities are changing in the situation? And you might also ask yourself, what quantities are being constant in this situation? Because that helps us. Okay, so are there any variables here that would be changing? And if so, we want to list what they are. Which ones are changing? Height, h. What else? Yep, good. Are there any quantities that are constant? Right. I'll also add area. What I want to do next is I want to use one of these formulas to find a relationship between differentials. A couple of differentials that I mentioned so far are dV and dH. But there's one more that I want to add too. They ask us about the rate that the mass of water is changing. So mass could have its own letter too, big M, let's say. And so the volume of water that's already there has a mass, big M. But that little slab of water, it has a mass too, dm. All right, so the mass is one more thing that's changing. We want to find how mass and volume and height are related to each other. How do their rates of change relate to each other, right? So I'm not going to be able to find that out by analyzing the area formula. These are things that are all constant. But these this is a mix of constants and changing variables. And so that's what I want to work with here, this formula here. So let's start with V equals LWH. I may want to identify which things are staying constant in the situation, which things are changing. So to do that, I'll say that V and H are variables that are changing. And L and W are just being constant. So what we want to do is we want to show that we could take a derivative of the things that are changing. One way to do that is to write just dv equals L W dh. Now the reason why something like that could be written hopefully makes sense from what we've done with implicit differentiation already. You're trying to take a derivative, but when you take a derivative of h there, the h could go away and the constants should stay, just like it would be if you were taking, let's say, a derivative of y equals 2 times 3 times x. Like, what would that be if you were doing a derivative? So you could get dy over dx equals 2 times 3, and then multiply that dx to the other side. Same kind of thing. Yeah, so we did the same thing, but we did it now with the volume and height. Differentiate implicitly first. Then divide by a differential of your choice. Depends on what the problem involves. And many of these problems will involve time. And so I'm going to divide the left side by a dt and divide the right side by a dt as well. This gives us related rates. So it talks about how volume could change with time and how that could be related to how the height of the thing is changing with time. Because when we go back to our problem, they had told us some information that we didn't use yet, and that's this: that the height of the water is increasing at a speed of 0.5 centimeters per second. So what are they telling us there? They're not telling us a volume or a height or a mass. It's dh over dt. That's what they're giving us here. It's a rate. You can tell because of the units. Height per time. So now we take that and we plug it in. 0.50 centimeters per second. And we can remove the L and W and plug in for them as well, because those things were given. So L is 10 centimeters, W is 12 centimeters. So let's multiply all that. I get 60 cubic centimeters per second. Great, so we're actually almost to the end. It's just that the problem didn't ask how the volume was changing with time. They went a little farther and asked, at what rate is the mass of the water increasing? So sometimes we want to think about, what are they asking? Like, what is the exact letter or letters that they're looking for? In this case, they are looking for something called dm over dt, the change in mass with time. So we have to know one more formula that could be relevant, and that would be a density formula from science. So the density formula says that your density will be your mass divided by your volume. But we can do the calculus version of that, and write dm over dv. And if we rearrange this formula, we can show that mass would be the density times the volume, or in other words, dm is the density times dv if we look at the differential relationship. So density is something that is constant for water. They gave us that in the problem. The density of water was stated to be 1 gram per cubic centimeter. So this is D. So let's use that. We're going to want to divide both sides by dt. And now we'll be able to find our answer, because right here we have dv dt. So this is going to get plugged in over here. And they told us above that the density was 1 gram per cubic centimeter. So that piece of information will be going here. Alright, so dm over dt is going to be 1 gram per centimeter cubed, 60 centimeters cubed per second. I get 60 grams per second.